Welcome to everyone. I'm Davide Xian, PhD student at Politecnico di Milano, and today I'm going to present NEPTUNE, Network and GPU-aware management of serverless functions at the edge. This work is carried out by our software engineering team composed of Professor Luciano Baresi, Giovanni Quattrocchi, Luca Terracciano, and myself. First, I'd like to give some background about two emerging computing paradigms: edge computing and serverless computing. Edge computing is a new computing paradigm for running workloads at the edge of the network. In particular, in our work, we deal with multi-access edge computing, which consists of edge devices offloading computations to nodes placed in strategic locations close to the end users. This allows lower network latency and bandwidth consumption, which in turn enables a wide range of applications, from self-driving cars to mobile gaming and IoT applications. However, edge computing raises some challenges. Edge devices are usually constrained by very strict low-latency requirements, and so it's important to keep the computation as close as possible to the edge client. For example, in the context of autonomous driving, low computation latencies are critical for the safety of the passengers. Achieving low latency consistently is easier said than done. Edge clients can move among different areas, and so the closest computing node can change over time. Then, compared to the traditional cloud, edge nodes are usually less powerful. Sometimes the closest node to the edge device may not be able to have enough computing resources for all the requests it receives, and so it's necessary to offload some of the requests to another node. Finally, workloads are very volatile and difficult to model. For example, if we consider the scenario of users moving to the stadium for an event, the workload can rapidly escalate in one zone. The other computing paradigm I'm going to introduce is serverless. Serverless is an emerging computing paradigm that abstracts servers from application development. In simple terms, servers are still there, but they are managed by a serverless provider. Serverless is also often associated with FaaS, function as a service. According to this service model, instead of serving applications as a monolith or as a set of microservices, applications are deployed as a set of functions. Serverless functions follow these three properties. They are stateless, so they do not have an internal state or they rely on external sources for state management. They are ephemeral, meaning that a function is expected to run for a very short time. And they are event-triggered, which means that they can automatically run in response to some events. Scalability is one of the main advantages of serverless functions. Differently from a monolithic application, where it's necessary to scale the whole application even if not all components are required to be scaled, in serverless computing we can scale each function independently. In particular, functions can be scaled in two ways: horizontally and vertically. Horizontal scaling means that the serverless provider can deploy multiple instances of the same function depending on their service demand. When demand is high, the provider can increase the number of function instances, and when it is low, the provider can decrease it. Functions are deployed on top of lightweight virtual machines or containers. These environments can be configured with the amount of resources, which usually are CPUs and memory, to run the function deployed on top of them. In the case containers are used, it's possible to vertical scale the containers at runtime, meaning that, while functions are still running and without interrupting their operation, it's possible to adjust the amount of allocated resources and therefore the computational power functions have. With respect to horizontal scaling, vertical scaling is faster. In horizontal scaling, creating a new function requires many operations, from downloading the function image to initializing the container and the application. This can take seconds, but also minutes. Vertical scaling is free from these operations and can allocate new resources within a few milliseconds. The work we propose, called NEPTUNE, tries to solve the challenges in edge computing while exploiting the serverless paradigm. NEPTUNE is an edge computing framework for serverless functions. It can manage large-scale edge topologies without any problem. It provides network latency minimization through smart placement and routing. If edge clients move, NEPTUNE can either spawn a new function instance close to the edge client, or if an instance is already present on the closest node, it can serve requests there. Sometimes node cannot host a new instance of the demanded function, and so NEPTUNE provides smart routing policies for offloading computation while keeping network latency low. Finally, thanks to GPUs and vertical scaling, NEPTUNE can also keep computing latency low. GPUs are used to accelerate complex applications, such as machine learning models or artificial intelligence applications, while vertical scaling is used to scale functions reactively according to their demand. NEPTUNE consists of a three-level hierarchical control architecture. The top level, called topology level, partitions a big edge topology into smaller communities. Then, the community level schedules functions and provides routing policies to minimize network latency. At the lowest level, the node level, NEPTUNE scales application to ensure functions have enough resources to keep computation latency as low as possible. Let's get into the detail of each control level. The topology level aims to lower the complexity of the placement and routing task, which is known to be NP-hard. This problem can be reconducted to the knapsack one. In the 2019, Polarakis et al. Demonstrated that the problem of placement and routing in an edge network has a non-polynomial complexity. To lower this complexity, we decide to split the whole edge network into smaller and closely located communities. To do so, we adopted SLAPA, Speaker Listener Label Propagation Algorithm, proposed by Xian et al. In the 2011. SLAPA has been proposed as a solution to discover overlapping communities in social network graphs. However, it has been also shown that it can deal with graphs of edge nodes. The main advantage of this algorithm is that it scales linearly with the number of nodes, and so it can handle also large clusters. We expect edge topologies to rarely change, and so the topology level computes new communities every few hours or days, or in response to events such as when a new node is added to the edge network or when it's removed. Once an edge topology is split into smaller communities, the community level provides an optimal function placement and routing policy. Scheduling and routing at the community level are done by solving a two-step mixed integer linear programming problem. In particular, for what concerns routing, and since GPUs are usually more powerful than CPUs, NEPTUNE prefers to send requests to node provided with GPUs and then to node with CPUs. So, how does the two-step mixed integer linear programming work? At first, we used only the first step optimization. The objective of the first step is to minimize the overall network latency. However, this can potentially lead to many function creation and deletions, which can affect service quality. Furthermore, we noticed that many solutions were close to the optimal one, but were characterized by fewer disruptive operations. So we decided to add a second step, which objective is to minimize the number of disruptive operations while maintaining an overall network latency similar to the one achieved in the first step. Finally, we have the node level, the last level of NEPTUNE hierarchical control. This level is based on the proportional integral controller, also called PI controller, which is a very famous and popular approach from control theory. The main advantage of this controller is that it provides good performance while having low and constant computational complexity. In fact, PI controllers are so computational lightweight that new resource allocations can be computed in a few milliseconds. In NEPTUNE, this translates into fast resource allocation and more responsive function adaptation. Furthermore, NEPTUNE assigns to each function one PI controller, and each function is independent of the others. However, sometimes resource contention may happen, and so we designed another component named Contention Manager that uses a fair and proportional policy to solve resource contentions. Then we implemented a prototype of NEPTUNE. The prototype has been built to work on top of either Kubernetes or K3s. Kubernetes is the de facto standard cloud solution for container orchestration, while K3s is a distribution of Kubernetes optimized for edge computing. NEPTUNE control levels have been designed as Kubernetes controllers, and function specifications have been modeled as a Kubernetes resource. In particular, we decided to describe functions as it is done in OpenFaaS, a popular serverless platform. In this way, the prototype is compatible with existing functions developed for OpenFaaS. Then, since neither Kubernetes nor K3s allows in-place vertical scaling, which means that it's not possible to resize containers without restarting them, we extended the orchestrator with a feature proposed by a Kubernetes enhancement proposer which enabled in-place vertical scaling. We also took special care when managing GPUs. Usually in Kubernetes and K3s, one function can reserve at minimum one GPU device. However, allocating a whole GPU to a single ephemeral function is often a waste of computational power. So, to provide an efficient usage of GPUs, we used the NVIDIA MPS to allow multiple processes to share one GPU. And we adopted the AWS Virtual GPU plugin to expose virtual GPUs inside the orchestrator. In this way, we are able to partition a single GPU into multiple ones, and functions can reserve a fractional amount of the original GPU. The source code of NEPTUNE is open source, and you can find the project at the link reported at the bottom of the slide. Finally, we assessed the performance of the NEPTUNE hierarchical control levels. We designed 3 types of experiments, and we ran our experiments on the AWS cloud. To have significant latencies, it has been chosen to deploy multiple nodes in different regions and availability zones. In particular, we choose 2 US regions, Area B and Area C, and 1 European region, Area A. Latencies have been measured using ICMP packets. In the figure, we reported the average latencies we obtained. We got from 85 to 95 milliseconds delay for a message to go and come back from a European node to an American one, and vice versa. The latency between the 2 US regions, Area B and Area C, has been measured to be about 12 milliseconds, while latency between different availability zones in the same region have been from 1 to 2 milliseconds. As you will see, we used a wide range of applications, and all experiment runs have been repeated 5 times in order to have robust results. The first experiment, called Moving Workload, has been motivated by the following research question: How does NEPTUNE handle workload generated by mobile users at the edge? The experiment has a duration of 60 minutes and consists in moving gradually every 10 minutes 100 users from one region to another. For this type of experiment, we used a simple application called prime numbers, which given a number n, it counts the prime numbers smaller than n. The focus of this experiment is to see how NEPTUNE behaves when users move among different areas and if functions move with users. In this chart, the workload is represented. We can see that it starts with 10 concurrent users and it goes to full speed at about 600 seconds. Then, at about 1000 seconds, the first migration starts and all users are moved from one region to another in 10 minutes. At about 2000 seconds, we have the second migration and all users come back to the original region. The second chart reports the average response time we achieved for the function. The dashed red line is the maximum response time we defined for the function. The dashed orange line is the set point we set for the PI controllers. And the black line is the average response time we obtained. We can see that NEPTUNE handles users moving from one region to another without any problem. Response times are really close to the set point and never beyond the dotted red line. This can be easily explained by looking at the allocated resources for each function. At 600 seconds, we can see that one function instance is not enough to take care of the whole workload, and so NEPTUNE spawns a new instance on a node in area A, the region where the workload is generated. Then at 1000 seconds, we have the first user migration, and NEPTUNE rapidly creates a new function instance on a node placed in the other region, area B. During the migration, NEPTUNE allocates one function instance for each region. This is because some users are still in the original region, and some have already been migrated. At the end of the migrations, since not necessary anymore, resources allocated at the original region have been all deallocated. In this chart, we can also observe the peculiar behavior of the two-step optimization. Since the second step is the one that minimizes service disruption, sometimes NEPTUNE can consider function placements less optimal than the best one. In fact, we can see that at the start of the user migration, pointed by the red arrow, the function is at first created on the node represented by the orange line. However, the workload arrives at the node represented by the red line, and so it starts suboptimally. But it rapidly understands the optimal solution. In fact, it proceeds to delete the instance on the orange node and it creates a new one on the red node. Finally, we monitored also the network latency. The chart reports the time spent by a request in the network with respect to the whole time needed to serve it. We can see that it's usually very close to zero, but in correspondence of the migrations, networking overhead increases. However, once NEPTUNE migrated the functions in the correct region, the network latency lowers back to very low values. The second experiment compares NEPTUNE with other state-of-the-art approaches. As in the previous experiment, we used a workload that ramps up from 10 users to 100 users. Each experiment have a duration of 20 minutes, and we decide to use as benchmark the application SockShop. SockShop is an open source e-commerce application composed by a set of microservices written in different languages. And to make the application suitable for NEPTUNE, the SockShop microservices have been adapted to functions. Then, as competitors, we decided to choose 3 state-of-the-art industrial solutions. To have a fair comparison, we chose to always use K3s as the edge infrastructure orchestrator. The first competitor is the default scheduler packed with K3s. Then we compared Neptune with the schedulers of two other popular serverless solutions, OpenFast and Knative. During the experiment runs, we monitored response time violation, networking overhead, and allocated resources for each function and for each approach. Results can be resumed as follow. Neptune on average achieves better response times. For example, for function orders, Neptune has an average response time of about 200 milliseconds, while other approaches have more than 400 milliseconds, more than the double of what Neptune achieved. Neptune reports also fewer response time violations. We can see that most of the time functions do not present response time violations. In the worst case, less than 3% of the requests have violated the maximum response time allowed. Other approaches present higher response time violations. In the worst case, K3s default scheduler and OpenFast fail to meet the desired response time more than 16% of the time, while Knative violated response time for function users close to half of the time. This can also be explained by the special attention we took when designing the network minimization approach at the community level. If we consider functions that require few computational resources, such as function payment, we can immediately see that the networking overhead in Neptune is lower than 10%, while other approaches has a networking overhead equal to more than 98%. Finally, if we consider how Neptune allocates resources in resource-constrained environments like edge computing, we can see that Neptune, as Knative, allocates at most just a bit more than one core, while K3s and OpenFast provisioned more than 4 cores to functions, exhausting in this way the edge network resources. The last type of experiment assessed the performance of Neptune when using GPUs. For this type of experiment, we benchmarked 2 instances of a pre-trained ResNet, a popular machine learning inference application. Since this function requires more computational power, instead of using 100 users, as for the previous experiment, we chose to set the maximum number of users to 30 users. The chart reports the response time of both GPUs and CPUs. As for the first experiment, the dashed red line is the maximum response time allowed, and the dashed orange line represents the PI controller's set point. The black line is the CPU response time and the blue line is the GPU response time. In the beginning, we can see that only GPUs are working. Then CPU's instances are created and we can see a spike in response time. This is due to the initialization of the container and the function environment. Despite the little spike, we can see that Neptune can recover well and allocates rapidly enough resources to keep computing latency close to the set point of the PI controllers. This experiment shows that our solution can run functions on both CPUs and GPUs, and it can ensure computing latencies on both of them. To conclude, Neptune is a solution for managing latency-sensitive serverless functions deployed on geo-distributed large-scale edge topologies. Results show the advantages of Neptune features, which are smart placement and routing, fast and fine-grained vertical scaling, and transparent management of CPUs and GPUs. Future work comprehends adding workload predictors so that instead of reacting to changes, we can anticipate them, achieving in this way even better self-adaptive quality. Then, it will be also very interesting to add state migration features so that Neptune can manage stateful applications such as databases. Thanks for the attention.